Hello everyone. So welcome to the second supplementary lectures on operator theory. So we were discussing the basics about what an operator is, and we saw the development of how we generalize the idea from a one-dimensional function of a real variable to functions of two variables, n variables, and then we generalize the idea to a matrix vector operations. So here you see a matrix acting on vector to provide another vector. So there we thought of the matrix as an operator, and then we took another limiting case where we allowed an case where the vector what we are taking as an input was from an infinite dimensional vector space, and then we have the realization of that an infinite dimensional vector space can be realized as a function. And using that idea, we came to appreciate the fact that an operator is any object that takes a function as its input, any function as its input, and provides another function as an output. Okay, and we also said that the set from which all these functions were chosen were part of a space known as function spaces. Okay, and then we covered some basic rules of operator algebra, where we said how the with respect to basic operations like addition operator, operators are associative and commutative. Okay, and then we said two special operators, the identity operator, null operators. We understood the concept of linearity of operators. Okay, so we'll take some examples right from here so that we get the more clarity on what we were what we mean. So let's take the first example. Okay, so let's say A is multiplication by x. So that means what we have in our mind is, remember, it is the operator acting on a function provides another function. So in this case, the operator, since is multiplication by x, that means what we have in mind is x times f of x is g of x. Okay, so that's a very simple example of what that operator can be. An operator can be as simple as just multiplication by let's say x here. Okay, another very useful example, and that I think so we have seen in disguise before in our calculus courses, where we can think about the derivative itself as an operator. So what we can do is we can ask, okay, so a hat is the derivative operator. Okay, so that means what the things that we are seeing is a hat acting on f is g of x, and this translates to the derivative of f of x is g of x. Okay, so we have seen how what characterizes a linear operator. So you see, an operator is linear if it satisfies this following rule. Okay, and remember, for example, the derivative operator, we have seen that the derivative operator, a ddx operator, is a linear operator. Why? Because exactly it satisfies that rule. Like if you know from our basic understanding of derivatives of functions, so if we want to take the derivative of a function, let's say alpha times f of x plus beta times g of x, this is exactly the same as alpha times derivative of f of x plus beta times the derivative of g of x. So here you see the derivative operator is hence a linear operator. Okay, because it satisfies the definition of linearity, as you can see. So this is the definition, the general definition of linearity that we discussed before. Okay, so those are some of the very basic and simple examples of what do we mean and what kind of operators that we'll be dealing with. In general, not all operators are linear, by the way. For example, I will give you another example, an example of nonlinear operator, and very common example of that is, let's say, the square root operator. I'll say that a hat is the square root operator. Okay. Now you can think about the idea, let's say, that if you want to take the square root, or let's write first it in terms of how we think about operators. So let's write it what we mean. So let's say we have a hat, and let's say why it's nonlinear. So let us impose a definition of linearity right away. So let's have f of x plus g of x, and if a is linear, this should become a hat f of x plus a hat g of x. Okay, and then let's test this idea whether this works for the square root operator or not. So remember, in this case, a hat is square root operator. Okay, and let's call this equation 1. So let's write the left hand side of equation 1, and so the left hand side, using the idea that the a hat is square root, it becomes the square root of f of x plus g of x. Okay, and you see what is the right hand side? You see the right hand side is square root of f of x, okay, plus the square root of g of x. And now you can readily see that for any generic functions, LHS is not equal to RHS, and hence the definition of linearity is not being satisfied. Okay, so that's a very important idea. So square root is a kind of an operator which is a nonlinear operator, as you can see here. Okay, so there can be various kinds of operators, linear, nonlinear, and we'll see more important ideas of various important ideas operator, where here we saw a case where the addition operator are being commutative. Like if you see, the operators a and b were commutative under addition. Okay, but we also discussed this fact that there are some operators, and in general, with respect to multiplication, the operators themselves are non-commutative. Okay, and we will see that idea coming next. Okay, so what we will talk next about is the commutative properties of operator. Okay, and the most important thing that we realized, I'll say, is in general, operators are non-commutative over the operation multiplication. Okay, so that's the generic idea. So what we have in mind in mathematical notation is, let's say we have an operator a hat and we have another operator b hat. So a hat b hat is not equal to b hat a hat in general. Okay, that means for any arbitrary operators a and b. Okay, that's what we meant. Okay, and based on this idea, that the product of two operators are non-commutative in general, there is a very important concept which is known as, or let's call that's the concept of commutator. Okay, and what this commutator does, the idea of this commutator is, it basically gives a measure of the degree of commutativeness of two operators. Okay, so what it does is, so the definition, or let's say we write, so this symbol square brackets a hat comma b hat square bracket close, this means the commutator, this is read as the commutator of a and b. This is the commutator of operator a hat and b hat, and this is the definition of that is exactly, the definition is exactly this what we understood here. It's a measure of the degree of commutativeness of two operators. So as you can see here, in general, a hat b hat is not the same as b hat a hat. So so the definition of this is basically a hat b hat minus b hat a hat. So in general, the commutator a hat, the commutator of a hat and b hat, this is not equal to 0. Okay, that is the most important idea that we are trying to come up with. Okay, that's the generic idea of what we mean by a commutator. Okay. As a special case of this, I will say, as a special case of this, there can be some set of operators that are commutative over multiplication. Okay, that means in that case, the commutator of a hat b hat acting, let's say, on a function gives us 0. Okay, and if this is true, then we say that a hat and b hat commutes. So let's take a very simple example where, this is an example. Let's say our first operator a hat is multiplication by x, and our second operator b hat is the derivative operator. Okay, so let's see whether what is the commutator of a with b. Okay, let's say this acts on some function phi of x. So let's find out whether the operators a and b commute or not. So if they commute, this thing will go to 0. So we have to evaluate what this is. Okay, we have to evaluate this quantity. So let's apply the definition of the commutator. So what that is a hat b hat e of x minus b hat a hat e of x. Okay, and let's now use the definition of what a and b's themselves are, which is, this is x, b is the derivative operator, minus b is the derivative operator, and a is x times phi of x. Okay. Now you see what is happening here. So this becomes x d phi dx minus, here you see, let's use the, because you see this is a product of two functions, x and phi of x, we can use the product rule of differentiation. So this will become x d phi dx plus e. Okay, because the derivative of x with x is 1. Okay, so if we simplify further, you see this becomes x d phi dx minus x d phi dx minus phi. So these two cancels. So what we are left with is minus phi. So what we shown was operator a and b acting on any arbitrary function phi provides, it's not 0, you see, this is not equal to 0, it's minus of phi. Okay, so therefore we say the operator a and b, that is x and ddx, the commutator of that is non-zero, and x and ddx do not commute with each other. Okay, and this idea is very important in quantum mechanics in general. Okay, quantum mechanics, if you remember the Heisenberg's uncertainty principle, can be or let's write it can be as it is a direct result of certain quantum mechanical operators that do not commute with each other. Okay, that's the basic, very basic understanding. Okay, that's one of the very important idea of commutator, and where commutator comes in handy in quantum mechanics, and we will see this later in later videos, that where this commutator comes in quantum mechanics. Okay, so we have a very good understanding of now about the degree of commutativeness, and that is expressed by the idea of a commutator. Okay, and based on that we will be able to tell whether two operators in general commute with each other. Okay, so now let's go to let's see another very nice little thing, which is, let's say, think about a situation whether when we have an operator a, you act on a function f of x, and let's say you get a result which is a scalar multiple of the function itself. Okay, something like this. So where this a is just a number. Okay, we have already seen one of such operators, a very trivial operator by the way, which is the identity operator. If you see, the identity operator acting on the function f of any function f of x gives a number which is 1 times the function itself. Okay, so we specifically want to look at these kind of operators which, when act on a function, provides the output which is a number times the function itself. Okay, and this equation where you have an operator acting on a function gives you a number times the function itself. This equation is known as an eigenvalue equation. Where the function f of x is called the eigenfunction of the operator a hat with eigenvalues a. Okay, so what we are dealing with is an eigenvalue problem here. So let's take a very simple example. So let's see, let's find out, let's say we have an operator A, which is the second derivative operator d2 dx2. Okay, and let's say we apply this onto a function. So let's find out the eigenfunctions of this derivative operator. Okay, so let's apply the definition of the eigenvalue equation, so which is d2 dx2 acts on a function should give us a times the function itself. Okay, so just by eyeballing the equation, you can see what we are looking at. We need a function whose second derivative is somehow related to the function itself. Okay, so we can think of one of such function is basically the trigonometric functions, if you think about it. So it's a sine some alpha x. Okay, and similarly can have b cos beta x. Okay, so if we substitute f1 or f2 in the eigenvalue equations, what we'll have is, let's write that down. So it's d2x dx2 f1 is a of f1. So you see this equation will be satisfied when, so this will be satisfied. So let's substitute this f1 here. So this will become the second derivative. So let's take the first derivative. So ddx of f of 1 is a alpha, derivative of sine is cos alpha x. Okay, that's the first derivative. So, and let's write the second derivative. So the second derivative of f1 with respect to x2 is a, and you get another factor of alpha, so it becomes alpha square, and cos, so that becomes minus sine alpha x. Okay, so let's now substitute this into the eigenvalue equation here. So that becomes minus a alpha square sine alpha x equals a times a sine alpha x. So if you see, what this implies is that the eigenvalue equations can be satisfied with f1 if and only if, a very important criteria, if and only if a equals minus alpha square. That means if you realize what was a, so this is the eigenvalue. Okay, that means what we are telling is the function a sine alpha x is an eigenfunction of the operator d2 dx2. Okay, the second derivative with an eigenvalue minus alpha square. Similarly for f2. Okay, so what we mean here is sine alpha x and b cos beta x are eigenfunctions for the second derivative operator. Second derivative operator with minus alpha square and minus beta square as the corresponding eigenvalues respectively. Okay, so that's the generic idea of what do we mean by an eigenvalue equation, and what is an eigenfunction for a given operator. Okay, so when you take an operator, you operate it on a function, the output that you get is a scaled version of the original function. Okay, that's you don't get any. So this is only very special functions. Only some special functions for a special operator will have this property. Okay, this will not be true for all functions. So that's why for a given operator, the eigenfunctions are very special, and we'll see later that the eigenfunctions acts as appropriate basis for function decomposition in general. Okay, so that's the generic idea of eigenvalue function. Okay, so that's the what we have covered in this small segment, where we saw the basic ideas of what do we mean by a commutator. We covered some ideas of a nonlinear operator, for example, let's say the square root operator, and then we came up with the idea of a commutator and how we measure the degree of commutativeness between two operators. We saw an example where, let's say, the function or the operator x and the derivative operators are not commutative. And then we saw we will discuss this in a little bit more depth in later segments about the relationship about, for example, the Heisenberg uncertainty principle in quantum mechanics with commutators. Okay, and then we discuss a basic idea about what do we mean by eigenvalues and eigenfunctions, and what do we mean by an eigenvalue equation. Okay, and we will see more specific concrete physical examples where these concepts will be understood better in later segments. Okay, so that's for this segment. Thank you.